All right, so let's start talking about circular forces. So in the last unit, we started to learn that forces actually cause acceleration, right? So let's go back and remember our definition of acceleration. Acceleration is the change in velocity. So it's a vector, and it really can mean three things. It can mean that you're actually speeding up, you're slowing down, but also it can mean that you're turning, because velocity is a vector, it has a direction, so if you change which direction you're going, even if you stay at constant speed, you're still considered to be accelerating. So we are going to be dealing with turning in this unit. So if we look at a circle, right, and we're saying like something's moving in uniform circular motion. So remember, that means that neither of these things are happening, but there is a constant speed. But if you have an object that's going around in a circle like this, at this point, say like right here, the velocity at that instant, if we were to freeze it, is actually tangent to the circle and it's pointing down. So the velocity right here is tangent to the circle and pointing down. If the object continues to move along, then we would have another velocity over here, which would also be tangent to the circle and would be pointing in this direction. So when something is pointing down and then it's pointing to the right, somehow it has had to turn, right? And if you're turning, that means that you are accelerating, and so a force must have acted upon you. And so if you imagine you're going this way and you want to turn this way, there must be some force that begins to pull on you that points in this direction, right? And because this is the direction of the force, this is also the direction of the acceleration of the object, right? So this force right here that is perpendicular to the velocity that makes something turn is called the net centripetal force, which we write within F sub C, and I'll just write it up here, is centripetal, not centrifugal. We'll talk about what that is in a second. So centripetal force. And it's a center-seeking force, and it is always pointing at any different position. So if it was here, it would be going up, right, towards the center of the circle. Right? And we actually call that acceleration, we call that also a centripetal acceleration. So if we write this in terms of Newton's second law, it says net force centripetal must be equal to mass times acceleration, right? Where this is a centripetal acceleration. So centripetal acceleration, we can actually calculate in terms of the velocity and the radius at which it's turning. So centripetal acceleration can be calculated by just taking the velocity, squaring it, and dividing by the radius. All right, so usually when I write Newton's second law, when we're talking about this uniform circular motion, I put that centripetal force, or the sum of the centripetal forces, or net centripetal force, is equal to mv squared over r, right? So in the last unit, I gave you sort of a process on how to walk through doing all of these Newton's laws problem, where the first step, remember, was to draw a free body diagram. So we're going to do exactly the same thing in this case. So I'm going to kind of switch to another page here, and we'll talk about that. So step one of Newton's second law problems for circular motion is to draw a free body diagram. And the free body diagram that we're going to be drawing in this case, we're always going to be trying to identify the forces that are pointing either in or out of the circle. So pointing in or out of the circular path, right? Then we ask ourselves, the second question is it accelerating? Well, when something is turning in a circle, right, the answer to this question is always going to be yes, because you're always turning, right? So it makes it easier. Before, we had to decide whether or not it was yes or no, and then whether or not we were going to set things equal to each other, or if we were going to do a sum of all forces equation. But here, the answer will always be yes. And so we write a net centripetal force equation, set it equal to mv squared over r, where this mass in particular is the thing that's actually doing the rotating, which will come into play a little bit later because we might have systems that have multiple masses when we get to some of our more difficult problems. And so just keep in mind that this m is always the thing that's actually doing the rotating, right? So let me just give you a couple of different examples, right? So let's deal with something that is being swung around in a circle on a string, right? So, and we're going to say it's a perfectly horizontal circle. So I've got like an object and there's a string attached to it and it's going around in this horizontal circle, right? And I'm just swinging it around. Right? So my free body diagram, usually they actually give you some sort of circle so you can kind of envision where the object is, or a picture of the object rather than just a dot, right? And so like at this position, we could identify the force as pointing into the middle, and what is causing it? Well, I said it was a string, right? So it's going to be called tension, right? And so this is my free body diagram, real simple, just like that. Right? Notice I don't put centripetal force on there. Centripetal force really isn't a type of force or like a practical thing that's causing a force. It's like saying net force, right? And we never used to put net force on our free body diagrams. We were always just thinking about like what's touching the object and what was exerting a practical push or pull in the real world. So here's a string and it's called tension. So is it accelerating? Yes. So if I wanted to solve this, I would just plug in and put my net forces that were pointing into or out of the circle right here. And I just say, okay, well, Ft is equal to mv squared over r. Okay. Let's do another example. Let's say I had a coin that's resting on a spinning disc, like a coin on a record player, which is really going to be a common example that we're going to use, right? So the coin is moving around in a circle, right? And it's just resting on the surface of this disc, right? So there's nothing touching it except the ground. So really what's keeping it from sliding is friction, right? So that must be pointing towards the center at this point. Here's my free body diagram. So now, is it accelerating? Yes. So I just do my sum of all forces equation. There's only one force. It is the force of friction, and that is equal to mv squared over r. Now, if we were asked about like the coefficient of friction, then just like we did before, we could substitute values in here and we could say, oh, well, I know that I can calculate friction. We know our equation for friction is this, mu Fn, right? And so if I wanted to substitute this in, I could have mu Fn is equal to mv squared over r, right? And this thing's on a flat surface, so I know Fn is Fg and Fg is mg. So mu mg equals mv squared over r. Sorry, I'm kind of running out of room there. But we're just looking at, performing those substitutions until we have things in terms of what we want. So look, we see the mass cancels for friction just like it did commonly in our last unit. But just keep in mind that really this is going to be the same exact thing over and over and over. We want to look at our free body diagram, identifying what forces are pointing into or out of the circle, right? And then do a net force and set it equal to mv squared over r, right? So in this case, we only have one force, so we're not adding or subtracting anything over here. But when we get a little bit more advanced and we start dealing with things that are moving vertically, then we might have tension and gravity acting in opposite directions, or tension and gravity acting in the same directions, and then we just add and subtract just like we did with other things. The last thing I want to leave this video with is talking about centrifugal force. So this is a common word that people know, and centrifugal is not a force. This term it's called a fictitious force, actually. And this is when we are experiencing feelings when we are in an accelerating frame of reference. So if you're sitting like on a merry-go-round or whatever, and it's spinning around in a circle, you are in an accelerating frame of reference. You are sitting in that thing, in that car, or like on that merry-go-round, and you are actually accelerating, right? So you feel this centrifugal force that you sort of feel like this, right? But that really is not happening. What is happening is you actually want to continue in your motion, right? So what you really want to do is you want to move tangent to the circle, right? And something like if you're in a car, the car door is pushing against you in this direction, causing you to turn, which is because there's a force in this direction, which makes you feel like your body wants to fly out. But really what you want to do is fly forward, and there's this center-seeking force that's causing you to turn. And we're actually going to watch a video, like a frame of reference video that talks a little bit about this, that hopefully will help to clarify that. So just remember, like, we will never talk again about centrifugal forces. They're not a thing. They're fictitious forces. There's some like figment of your imagination that is happening in a accelerating frame of reference and really isn't a physics force. The forces that we're talking about in this unit are centripetal forces.